oh, this is strange. It's just a small crowd. Nobody cares about channel coding. Okay, so let's get going. Oh, that's right. It's a strange UF schedule. I forgot. Turn off the camera. No, turn it off. Oh man, oh that's right, I forgot. It is odd. Okay. Anyway, while we wait another 4 minutes or whatever, fill in the blanks here. Cool.
That one over in, right?
What's that?
It's one trim, the link, the AVP, right?
What's that?
That one over in right here.
Sure.
Equality with the pi in.
Now this is a definition. These are all definitions. Yeah. This is the definition of empirical distribution. No, this is an identity. Yeah. Oh, that's a really important identity. Yeah. Yeah. So that's the definition of the empirical distributions. And equivalently, you know, when you take this mean, it's the same as that average. Yeah. It's just a. Just if you work out this sum, you'll find that with this definition, it's exactly that. It's really a cool fact. Yeah. That could slip by you. It's really important. Yeah. Yeah.
Distribution. You could have values that aren't just 1 over.
Well, this is the only definition there is. Yeah. This is it. This is the empirical the only definition you'll ever see of empirical distribution is that. Yeah. And I hate the language because really it should be empirical PMF. You know, but that's the language. That's, you know. Yeah. That's what I was saying in my email. The language is all over the place. It's not my fault. It's just, yeah. It's just, yeah. It's just that probably has been developed in so many subfields. They all developed their own language, you know. Different notation, different words, yeah. So it's just, that's life. Different symbols, yeah. 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 The simple way to see it is linearity. This really is a dot product, right? And dot products are linear. So that the dot product of L with pi n is just the 1 over n times the sum of the dot product of delta k with L. And the dot product of L with delta xk is just evaluation. Yeah.
It's like a sifting probability.
Sifting? I don't know what that
It's
means. That's
It's a signals and system concept.
I don't know, yeah.
A sifting function.
No.
That's what it's doing, right? It's just,
Yeah.
but it's sifting out probability.
Yeah.
Like a filter.
I guess. I don't know. Yeah. I don't know. Actually, it's time to, it's language I don't know, so. Shall we? Okay, so brave students of stochastic processes. So, first of all, some sad news. Not sad for me, but the last lecture wasn't recorded. Something went wrong with the equipment. So I'm tempted. I don't know if I want to promise anything, but I'm tempted to just give a lecture in an empty room so it can be recorded. Or perhaps one of the previous recordings from another year were better, although I change it every year. So we'll figure out what to do, okay? Because unfortunately it wasn't my best presentation. On the other hand, the notes are really good, so I don't know. We'll decide what to do. But let me just sort of give a quick overview in 30 seconds. So one big thing was the empirical distributions, and we were just discussing this. Well, first of all, this is dot product notation, which is just easier than having to write out the sum all the time. And the fact that that is just equal to the sample path averages, you get by linearity. Because you see this really is a dot product. If you take a dot product, taking a dot product is a linear operation. And we know that the dot product of any of these Dirac delta functions with L is just evaluation. So it's really, it is a very simple fact, but it's why it's so useful. And there's so many concepts, that's why it's very hard to present this in a very coherent manner. And I'm sorry it wasn't as linear as I would have liked last lecture. But we have a log likelihood ratio, which is absolutely fundamental to everything here. And I stuck in that it's minus the log of the reciprocal for a reason I'll explain in a moment. And there were these the geometry is really in these relative entropy balls. So given a model P, we look at all probability mass functions which are within some distance in quotes d from P. And that's a convex set, as we sort of proved. I mean, we really did prove it, but I don't want to formalize that, but it's convex. And then we, I refined the large deviation principle to answer questions like this. All right. So let's go back to the geometry first. So I've drawn a relative entropy ball here centered around P. Okay. And another relative entropy ball centered around Q, which we didn't talk about last time, but we can always do that. And the simplest hypothesis testing problem is solved by looking at a likelihood ratio test. We have ID samples. We want to say, did they come from P or from Q? And you look at this test statistic, and you ask, is it above a threshold or below a threshold? And so if you're above the threshold, it means you're in this half space, and you declare the samples came from Q. And if on the other side, you declare that the samples came from distribution P. So that's the simplest log likelihood ratio test. And I explained at the end of the lecture there are refinements. If you don't know Q, you can take this ball to be your test. If the empirical distribution's in here, I say P is true, and if they're outside, not. There are problems with that, but sometimes it's good. But one thing you can answer is questions like this. So what's the probability that your test says Q is true when in fact the distributions, the samples were generated from P? But first a question. Yeah. Yeah. Oh, you're trying to answer it. Oh, cool. Okay. So no, first I have to ask the question before we answer it. So this particular one, so this would be a probability, I called it probably a false alarm, because P is normal behavior and Q is abnormal. And what's the answer?
You can do minus ND.
N times D. Yes. So once you can draw the picture, you've got the answer. It's so cool, you know. And then the other one, it looks like, well, I didn't talk about that. It's not fair, you know. But that's why I stuck in this minus sign here, is that pretending that P is the center of the universe, well, I can always flip things around and say, no, Q is the center of the universe, you know, because these guys are just the minus of each other, you know. So when I look at this problem, I have this inequality here, that's the same as saying I could stick a minus sign in there and flip things around, you know. You know, so it's like minus L would be the likelihood ratio test if we considered, I mean, yeah, I say this. Minus L is just the reciprocal, P over Q, and that's when you thought that Q is the nominal model, all right? And that's what I'm saying here. I'm saying, suppose that the things came from Q, but you said, oh my God, it's got to be coming from P. You know, that's what this test would be saying. And what's that probability? Well, anyway, I mean, everything's symmetric, obviously. You know, so you're just basically looking at Q, the distributions are generated by Q, and I'm saying, what's the probability of being in this half space? And we know again, you know, that somebody, you know, that it's that subscript right there that gives you the answer. You know. All right, so exponential of minus n, and I chose the size of that ball to be epsilon. I didn't choose it. Given d, I grew this until it met. All right, so that epsilon, you know, is chosen so that these two balls just meet at this point here. All right, and Q star, you know, remember Q star. Yeah. And hold on a second. I just want to say this. I could write it in terms of P. I can also write in terms of Q. That's an exercise. But it's just because it's all symmetric, you know? I mean, it's just basically this hyperplane, you know, separates, separates P from this ball and all that. And the geometry is exactly flipped around. And the likelihood ratio, thinking that P is the center of the universe, is just minus the likelihood ratio of thinking that Q is the center of the universe. You know, so it turns out that you can express this probability measure here. We did it like this in lecture, but it could have been expressed thinking that Q is the center of the universe like that. Right? All right, and so from that you can get a weird formula for Q star is like it's some sort of geometric mean between P and Q. You can actually show that, but. Okay, but I've got to be organized. So what I want to do is, in the remaining 30 minutes, prove Shannon's coding theorem. You know, which just sounds crazy, but all I have to do is keep that picture, and we can do it. All right. I have to change things a little bit here, but. So the only thing absurdly ambitious is that I have to explain the model. And so you have to sort of, you know, pretend you had a few cups of coffee and wake up. And I'll write down the model and then we'll solve it because we've done it. You know, all the hard work's been done and at least, you know, giving a lot of confidence that you could understand the coding theorem and you can do most of the proof. So we have a what's called a memoryless communication channel. Press my way now. Okay, and it's memoryless in the sense that memoryless really means this, that the output at time k is some function of the input at time k and some noise, and that's IID. That's a definition of memoryless. And so from that you can get a coding model, the channel model. So the channel model is just given by this conditional distribution. And so that's given to you. You know P of y given x. All right? All right. And the setup is that we, why would we do this? Take about 5 courses in information theory, or 1 good course in information theory. But we just say the objective is to get bounds on the capacity of this communication channel. And to get bounds, we're going to generate code words randomly. So we're going to generate a code book. Wait a second. And which is which? Yeah. My notation. I've been nuts with this notation. All right, you see there's two integers here. There's the length of the word. So I've got this big long vector, and it might be 1,000, 10,000, I don't know. It's some long string of symbols. Maybe they're binary. So a binary channel would be these are 0, 1. All right, and I have capital N of them, which is going to be huge. All right, and in fact, N is going to be e to the nr, where r is called the rate. And that's not an integer, so if you want to, you can put a floor there or ceiling or whatever, the integer part of that. All right, and so how do we do this? So the idea is that we're going to generate these guys, their IID, with some distribution. All right, so we just, yes?
So the code book is a set of distributions?
No, a set of random variables.
So a set of random variables, and we're encoding a sequence like using one of those distributions?
Yeah, so yeah, that's right. So basically, I've got, so the sender has this code. So at the beginning of time, they generate this using the rand command, trillions of times. Okay, so basically you generate these strings, and the sender has this code book in memory, and so does the receiver, right? And every single one of these e to the nr code words corresponds to a real word in the dictionary, say. You know what I mean, or a phrase or something like that. So when you receive this abstract thing, you can look in your dictionary and say, oh, that means, hi, I'm going to bed now. All right? And so the bigger you can make R, the more stuff you're able to say in a time window from 1 to n. All right? So we'd like to make R as big as possible. All right? And so in this very weird case where you generate these code words randomly, we can compute using this geometry the maximum value of R. We can prove achievability. We can actually come up with a scheme for which we can reliably decode the signal, and it's just like a one-liner. I mean, I think most of you said, yeah, it's e to the minus nd. Well, you're done. You got the channel coding theorem. What's a miracle is that is actually the best you can do. Like if somebody came up with some weird fuzzy logic scheme to come with code words or use some other method, you couldn't do better. So that's the absolutely incredible thing. So I'm not getting to that. I'm just going to show that if you generate your code book through this IID scheme, then you can achieve what's called Shannon's rate. Yeah.
You mean the minimum value of R or the maximum value of R? Maybe the minimum.
We want to make it as big as we want it big, right? Because we want a lot of code words.
I mean, the larger the better, right?
Yeah, the larger the better. But then you might, if it's too big, I won't be able to tell what was
So
sent.
that's why we're looking for a minimum value of R.
No, the biggest value of R, subject to the constraint that I can get the probability of error being very small. Yeah, so basically we're going to look at this asymptotically. We're going to make n very, very large, and I want the probability of error to go to 0 geometrically fast with n. And there's a sharp cutoff for R, and that's Shannon's capacity formula. Okay? And it's just D. Yeah. That's right, yeah. All right. The only thing I have to erase is that. See, in order to put this in this framework, I've got to figure out I've got a hypothesis testing problem here, and it's not X, it's X and Y together. Okay, so I mentioned it last lecture, but let's say this again. So let's use, say, I star for what was really sent. Oops. Okay, so I as a sender know the I star was what I wanted to convey to the receiver, but the receiver just sees a string of symbols and has to figure what's going on. So what are the hypotheses again? This has to be written down just the right way. So the way I've set it up is wait, actually, be careful here. So given any I, so this is what's tricky. Before I defined hypothesis testing, we have a whole bunch of hypothesis testing problems. So I decided to make H1 the hypothesis that X that I was not the code word sent. All right. So that means that the joint distribution of X and Y is a product distribution, independent. Because remember, I generated all of these code words independently, and this noise is independent of everything else, right? So if code word I was not sent, then X and Y have nothing to do with each other. They're completely independent. So the joint distribution is a product distribution, right? And we're going to call that P. So in this hypothesis testing framework, we'll call that P. And so H2 is the other one. Okay, the notation of the book would be like this, you know. So it's the marginal, the probability of X, times the probability of Y given X, but that's just my channel model. All right. All right. So so you could see why I had to change the things around here a little bit. And I apologize, you have to go back to your notes and do this, but you're going to have to. Pi n now, if I can apply this machinery, our observations are the pair, and so we can't put an xi there. We have to put in a xi yi. You know, and little n there, you know, we're taking it to be, oh, it is little n, okay, yeah. It's very easy, sorry about that, little n. It's very easy to mix up the little n and the big N. The big N is the number of code words. So our observations are a pair like that. And so obviously here we would have xk, yk. That's all that would change, you know. It's basically we have a likelihood ratio now that's between these two possibilities, you know. And what comes out of this? Let's draw a picture. So P is the product distribution, and Q over here is the joint distribution, all right? Pxy, I mean the joint, you know, non-independent distribution. I drew this really big on purpose because that's how I'm going to choose my threshold. I'm going to take a tau which is really, really big and try to make it maximal in order to try to get R to be as large as possible. So I'll explain that now. So let's use a likelihood ratio test and play around and see if we can get some bounds, right? Okay. So we have this totally naive maximum likelihood decoder. So given a threshold tau, I'm going to, you know, just follow that diagram. So what is it going to be? So I dot here is the index that I'm saying this is the right index. That was what was sent. So if there's an I dot such that I'm over here for I dot, so I'm near Q, so I've got a P and a Q. So I'm near Q, that's the joint distribution. All right, this is a stupid test designed so it's easy to analyze. You know, you wouldn't really do this. But we pick a threshold tau, and we look at the empirical distributions for each. Remember, for every I, we have a hypothesis testing problem. So we have to look at these empirical distributions for every possible, well, I use I here, unfortunately. I'll make it into a K. There's a pi and I now, right? Because I've got an ID sequence of x's, I equals 1 through capital N, all right? So you go through and you say, if there's one for which I'm greater or equal to tau, and everybody else is less than tau, then I will declare I dot is the right code word, all right? Now, it's just for analysis, because you look at this and you say, why would I do this? I'll just take the maximum. You just maximize over I, and that would give you the right answer. So that's maximum likelihood. So this is sort of a hackish maximum likelihood decoder. You know, here again, I would take the max. I wouldn't have a threshold. It's just I'm trying to force this into the hypothesis testing framework. All right. You know, I mean, you could see this. I really want this to be maximal. That's really what I'm asking for. All right. The threshold here is just a tool for analysis. All right. So, but anyway, we can analyze this crappy test. You know, again, I'd much rather say I'll take the max over I and say that's what was sent. But here we're going to look at a suboptimal test and look at its performance. Can I erase this? I hate to. I need that diagram. Okay. Okay, let's get a bound on the probability of error. It looks tough because I've told you that we've got this enormous number of code words, you know, but let's do it. So there's two cases, there's two kinds of error. So the probability that so first of all, I star was what was really sent. And so what's the probability that I dot that with L, with my likelihood ratio, and it's less than tau? So where are we? So that's the Q situation. The true data is being generated by Q, all right? And I go over here and I look at the formulas we wrote down. It's been erased now, but we said the epsilon was the thing, the exponent. Okay, so that goes to 0 geometrically fast. Okay, we've dealt with that. The hard part is the other ones. Okay, so we're looking at the probability that one of these dot products is greater or equal to tau. That's a union. Whenever you see for some, say union, okay? For all intersection. All right, and so remember, sort of, basically, then you would, basically either you'd have an error or you'd say one of those guys is the right one. Yep.
I know what I star and Q star are the same.
What's that?
I know what.
No, I dot is not, might not be I star. That would be crazy. So really, I'm trying to get the probability that I get. I'm trying to get the probability that either I dot is not I star, or something crazy happened and the test failed because